Hi, I'm Coach Cowland, and in this presentation we're going to look at vectors and two-dimensional motion. Because we don't live in a one-dimensional world, we need to apply the kinematics that we learned originally in 2 and then 3 dimensions. Right now we'll just look at 2 dimensions. Because many of the kinematic variables that we use, such as velocity, acceleration, and displacement, are vectors and have magnitude as well as direction, we have to consider them very carefully in multiple dimensions. In one dimension, it's pretty easy to work out the direction because of the sign. If it's positive, it's going one way. If it's negative, it's going the other way. However, in 2 dimensions, the direction is given as an angle relative to one of the axes. Examples could be a velocity of 6.5 meters per second at an angle of 30 degrees above the horizontal, or an acceleration of 2.4 meters per second squared at 45 degrees east of north. These are all vectors that have magnitude and direction. Trying to do kinematics in 2 dimensions is a little complex. It's a lot easier if we split up our original vectors into vertical and horizontal components. That way we can deal with them one dimension at a time, and we can apply all of the stuff that we already learned in one dimension, apply it in the other dimension, and then put it all back together again. To convert a vector into its components, we use SOHCAHTOA. We know the sine of theta is equal to the opposite over the hypotenuse. We take our vector and turn it into a right triangle. Find the opposite side by multiplying the hypotenuse by the sine of the angle. We find the adjacent side by multiplying the vector by the cosine of the angle. This gives us our 2 components. If we have components that we want to combine into a vector, there are 2 steps to the process. The first part is to find the magnitude. We find the magnitude using Pythagorean theorem. A squared plus b squared equals c squared. So the vector is equal to the square root of the opposite squared plus the adjacent squared. But don't forget, we also need to find the angle. And we do that by finding the inverse tan of the opposite side divided by the adjacent side. Now we have the magnitude and the angle, we have the new vector. Occasionally we get a scenario where we need to add 2 vectors together, such as adding a velocity to another velocity. In this situation, simply adding the magnitude together just won't do. The first step is to find the components of each vector. Once we've found the components of each vector, we can combine the vertical components together and the horizontal components together. When we add the vertical components together and we add the horizontal components together, we get the components of a new vector, which is the sum of the old vectors. In the same way that we found the angle before, we can find the angle of this, and this will give us our new vector's magnitude and angle. We use all the skills that we previously applied in order to make this new vector. Let's look at a sample problem. Frank travels east 5 kilometers to one store before traveling north 8 kilometers to another. What is his displacement from where he started? First, I identify my data. Next, I list my variables and my unknown. My diagram gives a physical idea of what's happening. The first thing I do is find the magnitude of the vector. The displacement is 9.43398 kilometers. However, I only need 2 significant figures, so I round to 9.4 kilometers. Finally, I use inverse tan of the opposite over the adjacent to give me my angle of 58 degrees. In summary, Frank travels 9.4 kilometers, 58 degrees north of east of his original position. Let's look at another example. A plane is taken off at an angle of 20 degrees to the horizontal with a velocity of 30.0 meters per second. What is its horizontal and vertical velocity? First we identify the data. 20 degrees, 30 meters per second. Now we list our variables, known and unknown. We are looking for Vx, horizontal velocity, and Vy, vertical velocity. Drawing a diagram makes this a little clearer. First we solve for Vy, then we solve for Vx. Okay, so that's the end of the presentation. So what I need you to do is go back through it, make notes on everything that we've covered, complete the examples, check that you understand them, write down any questions that you have, things that you would like to go over in class. I'd like you to think of at least 2, and be prepared to continue on working on this in class, and I will see you then. Goodbye.